Here on Earth, we see light from galaxies billions of light years away. Based on this, it would seem that creation would be billions of years old. However, our next guest, Dr. Jason Lisle, presents a compelling argument to the contrary. Taking into account the speed of light and the passage of time in outer space, the evidence may surprise you. Stay tuned. Coming up next on Origins, distant starlight in a young universe with Dr. Jason Lisle. Hello, my friends, and welcome to Origins. My name is Don Chapman. It's such a privilege to be your host. You know, during our show, we showcase interesting guests who present evidence from science along with other important facts validating the truth of creation and the accuracy of the Bible. Today's guest, Dr. Jason Lisle, specializes in astronomy, physics, and apologetics. He has a PhD in astrophysics from the University of Colorado, and he has written books on the subject of astronomy from a creationist perspective. He currently works as Director of Research for the Institute for Creation Research in Dallas, Texas. Dr. Lisle, we are so thrilled you're with us today.
Thanks. It's good to be here.
So we're going to talk about distant starlight in a young universe. Help me.
Okay, this is an issue where the critics say, we've got you here, there's no way the Bible can be right because those galaxies are so far away, it proves the universe is billions of years old.
Okay, so we might as well go home.
Well, yeah, throw the Bible away and just go home. No.
But you've got some answers for us.
There's an answer to this. And let me summarize the problem here, and then we'll go through what I think the answer is. Distant galaxies are billions of light years away. Now, a light year is actually a measure of distance, not time. People hear the word year in there, they think it's time. A light year is 6 trillion miles. And so when we say that galaxies are billions of light years away, we mean they're really far away. They're very, very far away. It should take light billions of years to travel that distance, however. Light supposedly travels it takes 1 year to travel a distance of 1 light year, or 6 trillion miles. And so you'd think it would take light billions of years to get from those galaxies to Earth. Even though light's very, very fast, the galaxies are even further far away than light is fast, as it were. And yet we do see these galaxies. I have pictures of them. We have pictures of them on the screen here. And so the conclusion is, you'd think, well, billions of years must have elapsed. The light did get here.
Right.
It takes billions of years.
Right.
So the universe has to be at least billions of years old. Therefore, the Bible can't be true. Therefore, we might as well just go home. And
so that sounds like a very logical argument.
It does, but there are some assumptions that have been made. And that's always the case when people argue against Scripture. Either they haven't read Scripture carefully, or they haven't looked at the evidence carefully, or they've made some assumptions that have affected their conclusions. And in this case, we're going to see there's some assumptions that have been made that snag us. And before I talk about what I think the answer is, I want to very briefly hit some things that I think the answer is not. And the reason I do that is otherwise people will call in and say, well, haven't you thought of this? And the answer is, yes, we've thought of that. And there's a reason why that doesn't work. One solution that people have suggested is that the distances aren't real, that the galaxies, in fact, all of them are really close to our solar system. But that really just doesn't work. Observational science confirms that these galaxies really are at vast distances. I don't want to go into a lot of the details of that, but it's not based on evolutionary assumptions. No. There's good science that confirms these galaxies really are very far away. Yeah. One idea that's been tried is that the speed of light was greater in the past. And that's a good thing to test, right? That's a good assumption that should be explored. But in fact, I think it's not the case. We have good evidence that the speed of light, in fact, has always been what it is today, the speed of light in vacuum. In fact, the speed of light's tied in with other things in matter. Even the force between protons and electrons is related to the speed of light, interestingly. And so it appears to be a constant of nature that you don't want to tamper with, otherwise matter might not even be possible. Nonetheless, it's good to test these kinds of assumptions, because sometimes evolutionists assume rates are constant when they're not. But in this case, we think that it probably is a pretty good assumption. One that is very common is that maybe God made the beams of light already on their way, or the light in transit idea. And I've got a problem with this, though. This implies that God creates fictional images in movies. And let me explain what I mean by that. In 1987, we saw a star blow itself to bits, and you can see that on the left there is the star, and on the right is the explosion of that star blowing itself to bits. Now that is in a nearby galaxy. It's 179,000 light years away, which means in secular thinking, in conventional thinking, that event actually happened 179,000 years ago, and the light from the explosion finally reached Earth in 1987. Now, of course, some people would say, well, no, God just made the light on its way. But if that's the case, then that means that event never happened. It means that star never existed. It's just a picture in a beam of light that God made about 6,000 light years long. And finally, when it ran out, God made pictures of an explosion, and then it ran out. And today, we look at it, it looks like this little shape that you had there, that hourglass structure. That's the remains of that star. None of that exists if you believe that God created the light already on its way with pictures of these things.
So the light had a cause, and we can't illuminate that.
Yeah, if you believe that God created the light in transit, then the light was not caused by these things. Yeah, right. And so that's a problem.
No,
and
right, yeah.
and in fact, it's not just a problem for that. It would mean 99.9% of the universe is fiction. It's not something that actually exists. It's just beams of light that God created in mid-space, perhaps connected to an object, perhaps not.
God can do everything, but I don't think He writes fiction.
That's right. And again, that's my point too.
Yes.
I'm not suggesting that God lacks the power to do that. Of course He has got the power to do that.
It goes against the character of God.
Exactly. It goes against His character, against His nature. And some people might say, well, I don't know, I think God might do that. Well, be careful, because how do you know that you're watching us right now on the television? How do you know that I'm here right now if God's creating the beams of light right 1 inch away from your eye?
In touch with reality, yes.
Exactly. And so I don't think that is a Christian position, a position that's acceptable within the Christian worldview, I should say. A model that I think is a little more likely, a little more plausible, but I don't think it's quite the right answer, is that time dilation has allowed the universe to age millions of years while only 6,000 years has elapsed on Earth. And Dr. Humphreys and a few others have proposed models along these lines. I think that's a great idea to try. I don't think it's ultimately the right answer, because although it is true that time can flow at different rates in different circumstances, Einstein discovered that, and that's very well-tested physics. The effect tends to be very small, at least in terms of solving the distant starlight problem. It appears to be much too small to actually alleviate that difficulty. And so I don't think that's ultimately the answer. I could be wrong about that. Maybe others are working on it, but I don't think this is ultimately the answer. I think there's a better solution, and the solution that I think involves the one-way speed of light. You see, the speed of light is it's a constant, but that's a round-trip speed. And so let me go up to the board and I'll show you a hypothetical experiment that we could do to measure the speed of light. And so suppose that I'm standing over here and I've got a flashlight, and I'm going to measure the speed of light by shining the light down a really long hallway. Let's say the hallway's 186,000 miles long. We'll do it that way to make the math easier. Okay. We'll pretend we have government funding. We can waste it that way. And we'll put a mirror at the other end, or maybe I've got a friend at the other end with another flashlight. Either way. And what I'm going to do is, when the clock strikes noon, I'm going to turn the flashlight on for just an instant, send that light pulse out. It's going to go out, it's going to bounce off the mirror, come back, and then when I see it, I'm going to look at the clock and record the time. And it turns out that if I were to do this experiment, and that was the length of the hallway, it would take 2 seconds for me to see the reflection. That's how long it takes for light.
1 second down, 1 second back.
Now, we think 1 second down and 1 second back, but maybe that's not the case, and that's the point that I'm going to go into.
All right.
All we know for sure is that it took 2 seconds to make the entire trip. Okay, and so it had to go down, 186,000 miles, had to come back, so it had to travel that distance twice, and it took 2 seconds, and so we divide the distance by the time, and that gives us the velocity, and you find, lo and behold, light travels at 186,282 miles per second. And of course, a lot of people think, well, 1 second to go out. I'm glad you mentioned that, because that's what most people would assume. And in fact, I illustrated it that way, so I kind of led you.
That's how we did the math, right?
Yeah, I kind of led you to that conclusion. But in fact, this would still work if the speed of light was different going out than it is going back. For example, suppose the speed of light when it goes out is instantaneous. Maybe it takes no time at all to get to the mirror, and then it takes all of the 2 seconds to get back. Okay, now from my point of view over here, I would still see the reflection 2 seconds later.
Right.
The distance is the same. It's got to go out. It's got to come back. 2L, I divide. I get exactly the same speed, even though in fact the speed was instantaneous that way and was only half the speed on the way back. I'd get the same answer exactly. Or perhaps, alternatively, maybe it takes all of the 2 seconds to get out to the mirror, and then it travels back instantaneously for whatever reason. The point is, I can't know over here. In any of these circumstances, all I can see is that it takes 2 seconds for me to see the reflection of that light from the moment that I've emitted the beam. Again, the distance doesn't change, and the time doesn't change, and so the average velocity doesn't change. In all cases, it's 186,282 miles per second, the speed of light. And I hope you see where I'm going with this, because if it's the case that the speed of light when it's going away from us is slower, but then maybe it's instantaneous when it's back, you'd still get this for the average speed of light, and
Sure.
yet there would be no starlight problem because the light traveling earthward would be instantaneous. Now, some people have asked, well, why would the speed of light be different in different directions? And I don't really know, but then again, I don't know why it would be the same in all directions either. I mean, we don't really know one way or the other, and a good scientist doesn't say, well, I'd like it to be the same in all directions, and so that's the way it is. Well, we can't, make that assumption just without any kind of evidence. So what we really need to know is, what is the one-way speed of light? What is the speed of light just on one leg of its journey? That's what we'd like to know. Because if it's instantaneous when it's moving toward me, there's no starlight problem. So how would we go about measuring the one-way speed of light? We can't use a mirror anymore because we just want to do a one-way trip. So we're going to have a detector over here, and we're going to need another clock. We got a clock here to tell us when to start the journey, and so we're going to put another clock over there to tell us when the light arrives. Okay, and so I'm going to stand over here, and when this clock strikes noon, I'm going to send out my light pulse, and the other clock, when it receives the light pulse, it'll record the time. And in fact, I did this experiment in my office. Now, I don't have a long hallway, but I have the distance between my watch and my phone, and I can downstep the math and so on. And I found that when I did this experiment, as soon as my watch hit noon, I turned on the flashlight, the light went over, hit the phone read 12:05. And I said, light takes 5 minutes to travel from my watch to my phone. You're looking at me funny, you don't buy that, do you?
No, I don't buy it.
You don't buy that. Well, that is actually what happened, but of course my conclusion that it takes light 5 minutes to get from here to here would be a wrong conclusion, because in fact, obviously the clock on my phone is 5 minutes fast. It's 5 minutes
wrong.
ahead. Yeah. And so you see, the measuring the one-way speed of light would only work if the two clocks are synchronized. They have to read the same time at the same time. And it turns out, because we're measuring something that's very fast, these clocks have to be exactly synchronized. It won't be good that they're just close. It has to be exact, because if this one's just a little bit off, if this is 1 second off, your answer will be totally wrong.
Excuse everything.
Yeah.
Right.
And so we have to make sure these clocks are synchronized. And you think, no problem, we'll make sure the clocks are synchronized. Turns out, that's hard to do. Synchronizing two clocks that are separated by a distance, very hard to do. Now, the way most people will do this is they'll use a radio transmission. There's a radio station in Fort Collins, and it's hooked up to the atomic clock in Boulder, and it sends out a radio broadcast all the time. And in fact, this watch actually will receive that signal, and every night it synchronizes itself to the atomic clock in Boulder. Pretty neat. I don't have to set my watch. And so what happens is the radio transmitter at, let's say, midnight sends out the radio pulse, and then my watch sets it to midnight. But there's a problem here. That radio pulse took just a little bit of time to travel from the radio station to my watch. Now, it's not a long time. Radio's pretty quick, but it's a little bit of time. And again, these clocks have to be exactly synchronized. Now, if I knew how fast radio traveled, then I could maybe adjust that clock. I could say, well, I know it took 1 second to make the trip. I can make the adjustment, okay? So how fast does radio travel? Well, it turns out that radio travels at the speed of light. And that's the very thing I'm trying to measure, you see.
Oh, yeah, same.
And so we know that radio travels at the speed of light. And so some people have thought that if you put the clock, or if you put the radio transmitter in the middle, it'll work. But in fact, that doesn't work, because that assumes that the speed of light is the same, and the speed of radio, therefore, are the same in all directions. We know that radio is the same as light because they'll hit the wall at the same time. We know that. That's been measured. But since radio travels at the speed of light, it's impossible to exactly synchronize these two clocks that are separated by a distance. And putting the radio transmitter in the center doesn't help, because if the speed of light's different in different directions, then so is the speed of radio. And so this clock will get synchronized first, and then 2 seconds later, this one will get synchronized, and this one will be 2 seconds ahead of this clock. So you see, putting the radio transmitter in the middle doesn't solve the problem. Now, as a last resort, some people have said, well, maybe we could synchronize both clocks when they're together, and then we'll move one of them or move both of them to opposite ends of the hallway. And that seems to work. Of course, there's no problem synchronizing when they're both right there. Well, they're both reading noon. I can see that. And then you move one of them, and you say, okay, the clocks are synchronized, right? Wrong. There's a catch, because you see, the very act of moving that clock has caused it to become slightly desynchronized. According to Einstein, motion affects the passage of time. And so the very fact that you've moved one of the clocks causes it to become very slightly desynchronized from the other one. Now, we don't notice this in our everyday experiences because the effect is very, very small. And so you don't notice that your time is slowed down when you're walking as opposed to when you're stationary. But the effect exists nonetheless. It's a real effect. And so this clock is now very slightly desynchronized. Now, you say perhaps not all is lost, because in fact there's an equation that tells you how much the passage of time is affected by motion. And, but it turns out that in that equation is the one-way speed of light. And so again, you'd have to already know the one-way speed of light in order to know how much that clock has become desynchronized. Isn't that fascinating?
Yes.
And so basically the bottom line turns out to be this. The bottom line is that apparently it's fundamentally impossible to synchronize exactly two clocks separated by a distance without knowing the one-way speed of light. And of course, there's no way to measure the one-way speed of light without two clocks that are exactly synchronized, that are separated by a distance. And so what's happened here is we're caught in a permanent catch-22. You can't know the one-way speed of light without synchronized clocks, and you can't synchronize your clocks without knowing the one-way speed of light. And so it's a dilemma. We would like to know what the one-way speed of light is, because maybe that'll solve the distant starlight problem, but it turns out it's impossible fundamentally to know what the one-way speed of light is. And I'm going to suggest that implies that perhaps the one-way speed of light is a convention, and that's something that we can perhaps talk about on the other side of the break.
Right, we've got to take a break, but you've got a solution, so don't you go away. We'll be right back. We are back with Dr. Jason Lisle. Dr. Lisle, you left us in a dilemma.
Yes.
Would you restate the dilemma and then, for heaven's sake, solve it for us?
Yes, we've been trying to answer this question of what is the speed of light in one direction. We know it's round trip speed. That's easy. But how do you determine its speed in one direction? And what we found is, in order to measure the one-way speed of light, you'd have to have two clocks that are exactly synchronized. But it turns out, in order to have two clocks that are exactly synchronized by a distance, you'd have to already know the one-way speed of light. But you can't measure the one-way speed of light unless you have synchronized clocks, and you can't synchronize your clocks unless you already have the one-way speed of light. And so we are stuck in a permanent catch-22. Now, I'm going to suggest that it's not so much that there's a solution to this. There's an answer. It's not an answer that perhaps people would like, but I'm going to suggest that the one-way speed of light is a matter of convention. And a convention is something that we all, human beings, we agree to it, and it works as a result of that. As long as we stick to it, everything works. Like the number of inches in a foot. Now, I don't know historically why there are 12 inches in a foot, but somebody decided there should be 12 inches in a foot, and we all agreed to that, and so it works. As long as we stick to that, it's fine. Driving on the right side of the road is a convention. We all agree to it, and it works. You don't agree to that, you got problems, right? Yes. But on the other hand, if you go to a different culture, you go to Australia, everybody drives on the left side of the road, and they agree to that, and
that's
that
a different
works.
Convention. That's
exactly.
Right.
And so I'm going to suggest the one-way speed of light is like that, because it's not something that you can measure without already knowing it. That suggests it's kind of like inches in a foot. It's not something the universe determines or something that God has determined. It's something that He leaves up to us, interestingly. And so it turns out you can actually define the speed of light, the one-way speed of light, to be basically whatever you want it to be within certain constraints. And that will tell you then how to synchronize clocks. And then when you go to measure the one-way speed of light using your now synchronized clocks, it will be whatever you chose it to be.
Huh.
So it's a convention, interestingly. And this principle is called the conventionality of distant simultaneity, or sometimes just the conventionality thesis. And if folks want to look that up on the internet, that's what they want to research. And this is actually a pretty well-established principle in physics. Now, not 100% of physicists agree with it, but most of us do. Most of us who are trained in relativity. The fact that the one-way speed of light is not measurable, and in fact is something that we human beings get to choose. And what that means is, since I can choose the one-way speed of light within certain constraints, then I can then have a synchrony convention. Now I can synchronize my clocks, but it's a bit circular.
To the conventional standard, yeah.
Exactly. And it doesn't mean that the other conventions are wrong, they're just different. It doesn't mean that driving on the left side of the road is wrong in Australia. No. It's just a convention that they use. Whatever convention you choose, if you're consistent, any experiment you do will verify your choice. And so what most physicists do then is they'll choose the speed of light to be the same in all directions because it makes the math easier. But that's the only reason. It makes the math easier. You don't have to make that choice. In fact, let's suppose you had two bolts of lightning that strike at the same time, or they're expected to strike at the same time. And that's the prediction. And you want to say, I wonder if they really are going to strike at the same time. What I'm going to do is I'm going to go stand directly between the two lightning bolts, okay? And they're separated by a distance. And I've got mirrors here so I can see both directions simultaneously, right? And if they strike at the same time, the light will come to me. And if they strike at the same time, I'll see them at the same time because I'm exactly in the middle. But that, of course, assumes that the speed of light is the same in all directions. Now, of course, I'm allowed to stipulate that. I'm allowed to choose that as a convention. And so he says here, if only I knew that the light by means of which the observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M. If only I knew that the speed of light's the same in all directions. But an examination would only be possible if we already had at our disposal the means of measuring time, if we already had synchronized clocks, which we can't do fundamentally. It would thus appear as though we are moving in a logical circle. That's that catch-22 we've been talking about. That light requires the same time to traverse the path A to M as the path B to M is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. What he's saying is, I can choose the one-way speed of light to be the same in all directions if I so wish to do so, and that will tell me how to determine synchronized clocks. That's my choice. But if somebody else wants to make a different choice, they can do that too. It's something we stipulate of our own free will. And that is a quote by Albert Einstein.
Oh, wow.
Yeah, Einstein realized that the one-way speed of light is not a property of nature. It's something we get to choose. And that tells us how to synchronize.
Same thing, yeah.
Exactly, yeah. And he writes about that in Relativity, his premier book on relativity. And so what this means is there's more than one way to synchronize clocks, and therefore the speed of light in one direction can be different depending on which synchrony convention you choose. Most physicists choose what Einstein did, the Einstein synchrony convention. They choose the one-way speed of light to be the same in all directions because it makes the math easier. And in that convention, light does take billions of years to travel billions of light years. But I want to suggest to you that there's another convention that we could use, the anisotropic synchrony convention. Anisotropic means different in different directions. And under this convention, the speed of light when it's moving directly toward you has infinite speed. Okay, it takes no time at all for light to get toward you because that's how we're choosing to synchronize clocks. Okay, so when the light passes by this clock, it's noon. When it passes by that clock, it's noon. When it reaches you, it's noon. And therefore, it takes no time at all for the light to travel that distance. And I want to suggest to you that, well, of course, if that's the case, if we define time that way, then we're looking at the universe in real time because the light, as soon as it's emitted from the star, it reaches your eye, taking no time at all to get from there to here. And that's an anisotropic synchrony convention. Now, if you were to shoot light back out, it would take a long time to get back because we know the round-trip speed of light. That's something that's set by God. That's 186,000 miles per second. You can't change that. But the one-way speed we get to define. And I want to suggest to you that this anisotropic synchrony convention is in fact the one that is used in Scripture because, first of all, it was the one that all ancient cultures implicitly used. They did not subtract off light travel time. When you see something happen, that's when it happens in terms of their understanding of space and time. And of course, I also want to suggest to you that the Bible is using this anisotropic synchrony convention. Partly because, again, it's the version that all ancient cultures would have used, but also because of the way Genesis is worded. If you take a look at Genesis 1, 14 and 15, God here is describing the creation of the sun, moon, and stars, also the lights in the heavens. Then God said, "Let there be lights in the expanse of the heavens to separate the day from the night, and let them be for signs and for seasons and for days and years." And he goes on to say, "And let them be for lights in the expanse of the heavens to give light on the earth." And it was so. What was so? Well, God made the lights, and they gave light on the earth. Apparently, the very instant that God created the stars, they immediately began giving light on the earth. Their light reached the earth instantaneously. And that suggests the Bible is using this anisotropic synchrony convention, because under that convention, which is perfectly compatible with all physics that we know about, light takes no time at all to travel from those distant galaxies to Earth. It can reach the Earth just like that. So what that means is the universe is not billions of years old just because the galaxies are billions of light years away, because the Bible's using this anisotropic synchrony convention in which we see the universe in real time. Light from those galaxies reaches Earth instantaneously under that convention. It doesn't mean the secular convention is wrong. It's just different, and it's not the one that the Bible uses. So my point is, the secularists really can't say, well, we know that light takes billions of years to get from there to here, therefore the Bible's wrong, because the Bible's using an anisotropic synchrony convention, in which case it takes light no time at all to get from those galaxies to Earth.
Huh.
Yeah.
That's amazing. So, is this what you believe's happened? Do you believe you believe your convention is that?
I think this is the right answer.
This is the answer.
I'm convinced by verses like Genesis 1:14 and 1:15 that the stars did immediately fulfill their God-ordained role to give light upon the earth. He spoke and they stood fast.
Yes.
And they immediately fulfilled their God-ordained role of giving light upon the earth.
They obeyed him in an instant.
Yeah, exactly. And that is the convention that all ancient cultures would have used, the Bible meaning to be understood by many different cultures, not just modern physicists. I think that's the convention God would use. And the neat thing about this is this is known physics. This isn't some crazy creationist coming up with these new ideas. Albert Einstein realized this, and secular physicists would realize that indeed the one-way speed of light is conventional, and therefore there really is no distant starlight problem. There never has been, ironically.
That's absolutely astounding. So we've been intimidated by a problem that doesn't exist.
That's exactly right. Well said. Yeah. And of course, I've written about this, and people can check out our website, ICR, and
put a plug in.
Okay, we've got. I have a chapter in the book, Creation Basics and Beyond, and in that resource, people can read in more detail what we've just talked about today. And I've published papers too in the peer-reviewed literature, and nobody's been able to refute this. So I think we have a very good answer to this in Starlight.
Isn't that amazing?
Yeah, it is.
Folks, I hope that beyond just the answer of light, that your confidence has been buoyed today. That as you hear Dr. Lyle say, there really isn't a problem here, and that God's answer stands firm. I hope it's made your faith more confident. You know, it's God's view that He created you, and that should always be your worldview too. I hope you'll join us again soon here on Origins, and until then, God bless you, my friend.
Thank you for watching this edition of Origins. If you'd like a copy of the PowerPoint information presented today, you can download a PDF file from our website at originstv.org. Or for a DVD of this series, you can order online or send a $12 donation to cover shipping and handling and write to Origins Program, number 1601, Cornerstone Network, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and financial support of you, our Cornerstone family.